Hi everyone, this is a lesson on continuity of functions and the connection of continuity to one-sided limits. When we see a graph like the one pictured here, it's the type of picture that bothers us. There's problems with that graph. We like to see nice, smooth graphs. This graph is kind of the opposite of smooth. It has holes in it. There's a jump. When x is 2, the y value abruptly jumps from a y value of 2 to a y value of 3 right in this region. So we look at this and we're bothered by it because it violates some of our expectations, and actually what those expectations are expectations of continuity, the function being continuous. So what we'll do is we'll define continuity, we'll define what that means for a function to be continuous, and then look at the various ways that a function can violate continuity. Pictured here is a function with a bunch of different problems. If you want to think about lack of continuity as a problem, and I certainly do, the function has a problem at x equals a, so in this region here. What's happening there is that the value of the limit as x approaches a of f of x is this point there. But the value of the function itself at exactly a is up there. So the value of the function at a is not equal to the value of the limit at a. That's one type of discontinuity. At x equals b, there's another type of discontinuity. The limit as x approaches b is given by that y value. So we'd read that across and say, well, that's the y value that we'll get at that point. But the value of the function itself at x equals b does not exist. There's no filled in circle above or below that hole that's been cut into the graph. So the limit as x approaches b of f of x exists, but f of b does not exist. So that's related to the first discontinuity at x is equal to a, but it's a little bit different. At c, there's a different problem. There's a jump in the graph. The graph goes abruptly from a y value of that, whatever that is, to this y value, whatever that is. It's not continuously changing from a lower y value to a higher one, or from a higher one to a lower one. It's abruptly jumping. This is called the jump discontinuity for obvious reasons. But we need to be able to describe it algebraically, and our description is going to be in terms of limits. We would say that as x approaches c, from the left-hand side, we're not going to get the same height or y value as we would get if we have a limit as x approaches c from the right-hand side. You can think about it as two different math cars. A math car on the left side, approaching c, is going to see a height of, let's say, 2. And the math car, if we put a math car on the right, and push it to the left, it's going to see a different height, let's say a height of 5. Those two math cars see different heights as they approach that same x coordinate, so we would say that the limit as x approaches c doesn't exist. The left limit and the right limit, and I'll show you what the terminology or notation is for that, the left and right limits don't agree. So the two-sided limit, or the old limit we were just talking about in previous lessons, that limit doesn't exist at c. And that is how we would algebraically indicate that a function has this type of discontinuity at a point. The last one, at x is equal to d, in this region here, what's happening there is as x is approaching d from the left-hand side, the y value is going higher and higher and higher. It's approaching positive infinity. As x approaches d from the right-hand side, it's going lower and lower and lower. You can go back to math cars if you want, with the math car on the curve. Push the math car towards that x coordinate d, that the height of that car goes higher and higher and higher, like the elevation keeps going up. Whereas on the right-hand side, you stick the math car on that side and push it towards the x coordinate of d. As long as that car stays on the curve, you'll see that its elevation gets more and more negative. So this has some relation to the jump discontinuity, because what's happening on the left side is not the same thing as what's happening on the right side, but it's distinct because both of those limits from the left and from the right are not giving us numbers. They're giving us plus infinity on one side, minus infinity on the other side. So we don't call this one a jump discontinuity, we call this one an infinite discontinuity. Or you may have used the term for vertical asymptote, which is a term that we're going to use in this course as well. So that's highlighting all the different problems with the graph and how we would explain them algebraically, how we would pose them in terms of the limits. And I'll talk about left and right limits in more details next. So this is a simpler graph. It only has one problem. And that problem is happening in this case at x equals 0. I'm going to look at the picture first, then look at the definition of the function algebraically. So the picture, you imagine the math car on the left-hand side. You're pushing that math car towards the x-coordinate of 0, and it finds a height of 0. So C's height of 0 as x approaches 0 from the left. So we indicate approaching a number from the left-hand side by putting that number and then a minus sign in the power. So if we were approaching 2 from the left, it would be x approaches 2 with a minus sign in the power of 2. So 2 to the power of negative. It's not 2 to the power of a negative number. It's just a shorthand that means we are approaching from the left of 2. Why is it negative? Well, think of the number line. Your number line goes from negative values to positive values. So it goes from small numbers to large numbers. If I'm approaching 2 from the left-hand side of the number line, that means I'm approaching 2 from a number like 1.9, from something a little bit less than 2. So 2 with a minus on it would be 2 subtract a tiny amount. 0 with a minus as the power means 0 subtract a tiny amount. If we put a math car on the other side and push that math car towards the x-coordinate of 0 from the right, we get a different height. We get a height of 1. So this math car sees a height of 1 as x goes to 0 plus. So for right limits we put a plus sign because it's that number plus a tiny bit. These two math cars do not agree with each other. Whenever that happens, whenever the limit from the left gives you a different y value than the limit from the right, we say that the two-sided limit does not exist. The two-sided limit, so I'll put down one-sided limits. There's two of those. Limit as x approaches a from the left of f of x. Limit x approaches a from the right of f of x. Those are approaching the value, or approaching an x-coordinate from the left or from the right, so one at a time. And the two-sided limit is approaching from both sides at the same time. Two-sided limit, that's the limit as x approaches a of f of x, which means approaching from a minus and a plus at the same time. So you're asking it on both sides. What's your y value as you come from the left? What's your y value as you come from the right? And if those numbers aren't the same, then that limit doesn't exist. All right, so let's answer the following questions from the graph. And this is a valid and normal, and I want to say standard test and exam problem. Just a different picture and different numbers. We're asked for the top graph, and I'll put a line here just to help distinguish these. For the top graph, we're asked, what is the value of the function when x is exactly 2? That's f of 2. So we go to an x value of 2, and we're looking for the filled-in circle. And that filled-in circle is happening on a y value of 5. Remember, when you plug a number into a function, you get a y value. When you perform a limit on a function, you also get a y value. So anyways, this is a function evaluation, looking for the y value when x is exactly 2, and the answer is exactly 5. Next, what is the limit as x approaches 2 from the left of f of x? So I'm going to draw a math car there. And push that math car from the left-hand side of 2, and then ask, what's the y value going to be? And it's going to be a y value of 4. It's going to get closer and closer and closer to that y value as I push the math car to the right and approach that x-coordinate of 2. How about 2 from the right? 2 plus. Well, now I have to go to the right of 2, put my math car down, push that towards 2 from that side and ask, well, what is the y value going to be there? And the y value is going to be 1. So I'm reading from the y-axis. Now the last, what is the limit as x approaches 2? Well, that's a two-sided limit. We approach from the left and from the right simultaneously. It does not exist, DNE, since limit x approaches 2 from the left of f of x does not equal the limit as x approaches 2 from the right of f of x. Those two limits don't equal, and whenever that happens, we say the two-sided limit does not exist. All right, next problem. f of 2. So we go to an x value of 2, and then we go up until we see the filled in circle, and we quote off the y value. So the y value here is 5. Now the next piece, we're taking a limit from the left, so I'm going to draw a math car to the left of that point on the curve and push that math car towards that x coordinate, and the y coordinate that I read is 4. Then on the right hand side, for the right limit, for the next part, limit as x approaches 2 plus, I put a math car on the curve just to the right of 2 and push it towards an x coordinate of 2 and read off the y value, and it's going to get very close to 4 as well. Then the last part, limit as x approaches 2 of f of x, that's the two-sided limit. I'm asking approach from the left and approach from the right, what y value do you see? Well, this time they agree with each other. The math car on the left side and the math car on the right side both say 4. So the answer is 4. It exists. So that's how you tackle these graphs. And I'm focusing just on one point. We could do the same thing for a function like this one that has many points, examining one point at a time. Now the connection between limits, I kind of already ruined the surprise. The connection between limits and continuity is in the different mix of responses you have to values, to evaluations of the function and evaluations of these limits. It turns out that one second. So it turns out that we can define continuity in the following way, that we can exclude all these different types of discontinuities if we have the following properties. Oh, I'm getting ahead of myself. Sorry. So this is just to talk about one of those two properties, not both of them, just the first of the two properties we will need to define continuity. We will need the two-sided limit to exist at a point for the function to be continuous at that point, but that's not enough. So to put it formally, I wrote it, but it's good to have it written down in a more careful way. We can say that a function's limit as x approaches a of f of x equals L if and only if the left limit as x approaches a, so x approaches a from the left, a minus of f of x equals L, and the limit as x approaches a from the right, a plus of f of x is also equal to L. So those two limits, left and right, are equal to the same number, L. Then the two-sided limit is also going to be equal to L. So that's one piece we need to define continuity. We need the two-sided limit to exist. The other piece we need is we need that value L to be equal to the value of the function at that point. And you can think about the second example here, the one on the bottom. That function has a limit that exists, but it fails to be continuous because the value of the function at x equals 2 is 5. The value of the limit as x approaches 2 is 4. 4 and 5 are not the same, and you can see from the graph that there's still that problem, that hole that's been cut in the function and filled in somewhere else. So in order to capture all the necessary ingredients to exclude all types of discontinuities, we need the limit to exist, so left and right limit must be equal, and we need that number to equal the value of the function at the point. Now, for the value of the function, for the value of function at that point to match the value of the limit, first of all, we need the value of the function at that point to exist, so it has to be a number that's in the domain. So if, for example, if you have a hole cut into a graph and it has not been filled in above or below that hole, then there's nothing you can do about imposing a continuity requirement at that point. You may have a value of the limit at that point, but you don't have a value of the function at that point, so you can't say that the value of the function is equal to the value of the limit. Anyway, that statement at the bottom is the grand statement of continuity, that the limit as x approaches a of the function is equal to the value of the function at that point. But remember, contained within this statement is the left and right limits being equal. This existing requires that the limit as x approaches a from the left of f of x equals the limit as x approaches a from the right of f of x. And that's a guarantee. If this requirement is not met, then that's a guarantee that the function has a discontinuity. So let's look at this function and match this function against the requirements to see if it's continuous at, in this case, it's asking us what's happening at x equals 1. So it's asking, is the function continuous at this particular coordinate? And to answer that question, we have to look at the definition. So definition. F of x is continuous at x equals 1 if and only if the limit as x approaches a of f of x equals f of a. Now I'm going to replace the a with a 1 since the question gave us a particular number. So limit as x approaches 1 of f of x is equal to f of 1. And then answer the question. F of 1 is the easiest one. This piecewise function says that if x is equal to exactly 1, then the y value is going to be exactly 42. Now the limit is a little bit harder. That's the limit as x approaches 1. A limit means we're not plugging 1 in, we're almost plugging 1 in. So it's like plugging in 0.99 or plugging in 1.001. 0.99 is not equal to 1. 1.001 is not equal to 1, so those get plugged into the top part of this piecewise function, which corresponds to x value is not equal to 1. So x squared minus 1 over x minus 1. This is a 0 over 0. We have to factor. So x minus 1 times x plus 1 over x minus 1. We can cancel the x minus 1 top and bottom, and we get 2 equals 42, which is false. So it does not equal 42, does not equal 42. So the limit as x approaches 1 of f of x does not equal f of 1. Thus, f of x is not continuous at x equals 1. What does this function look like? Believe it or not, it's actually a straight line. It's a straight line that has a slope of 1 and an intercept of 1 with a hole cut into it. I have a picture of it. Well, I don't have a picture of it, but I'll just quickly draw one. Oh, I'll be careful. When x is 1, there's a hole. When x is 0, is equal to 1. So something like this. So a hole's been cut into the graph at x equals 1. And then it's been filled in up here at 42. So that's what this graph looks like. Now, what happens if we change it? What if we change the function so that instead of the piecewise part at the bottom, for x equals exactly 1, instead of that being 42, what if it's equal to 2? Well, in this case, we've already done the limit. We did the limit of the top part. Limit as x approaches 1 of f of x. We got 2. The value of the function is 2. That means that the limit at x equals 1 is equal to the value of the function at x is equal to 1, since 2 is equal to 2. So that means that this function is continuous at x equals 1. It meets the definition of continuity. And this f of x is identical to f of x equals x plus 1 for all x. No holes. It's identical. It has the same graph. This is a really weird way to write it. We'll continue in the next video.